the theory behind titrations and carrying out titrations. Now, you know that a titration is a procedure that we do in a lab that involves the use of a burette and a pipette. We're using burettes and pipettes because they're very accurate pieces of equipment or accurate bits of apparatus that we use to measure volume correctly or volume accurately. We also use a volumetric flask. So all of these reagents, I suppose, or the things that we're using as reactants are all liquids. The acid is a liquid, the base is a liquid. And therefore we have to know the volume of those liquids that we're reacting together so that we can calculate the concentration then of whichever liquid, whichever reagent, whichever acid or base, whichever we don't know the concentration of. So do you remember I would have said to you that when you're doing a titration, when you're carrying out a neutralization reaction, so you're reacting an acid and a base, you're carrying out that in as a part of your titration using the burette and the pipette. So you have to know about the procedures or the precautions involved in preparing the pipette, preparing the burette, all of that really well, okay? Now, when we're doing a titration, we have to know the concentration of either the acid or the base first. If you don't know the concentration of either, you're going nowhere because you have two unknowns then in your titration. So you won't be able to calculate the concentration of the acid, say. Okay, so we started off in 5th year. We prepared a standard solution of sodium carbonate. And with that standard solution of sodium carbonate, we knew the concentration of the sodium carbonate. We were then able to use that sodium carbonate to titrate against an acid solution that we didn't know the concentration of. The purpose for the titration is to calculate the concentration or the molarity of the acid. Okay, so I'm going to do a calculation in a separate video, but for the moment I just want to do the theory here. Okay, so what's a standard solution? It's a solution of precisely known concentration. This is all starting on page 89 of your revision book, and you have it in your notes. And we also filled out some revision sheets as well, where we wrote out the procedures and all of that. So you should have this in a sort of revision sheet in your folders as well. So a standard solution is a solution of precisely known concentration. And when you want to make a standard solution in chemistry, you need to use a primary standard. And the criteria of primary standards would be substances that are available in pure. Remember we had pure, soluble, stable, solid. So 3 S's and pure. So that what can we do? We can weigh out a certain amount of it and we can dissolve it in a given volume of solution. And we now then have a solution of accurately known concentration or precisely known concentration. The primary standard that we used for acid-base titrations in 5th year was sodium carbonate, anhydrous sodium carbonate. Be careful now, if they ask you to name the primary standard, you must write it out in words. Anhydrous would have to be there too. So you'd have to write out anhydrous sodium carbonate. Okay, right. Now, just very quickly now I want to run through the PowerPoint. So the volumetric flasks, you're familiar with those. Now, how do you prepare a standard solution of sodium carbonate? So you'd say using, watch it, you're using your apparatus. So using a dry, clean clock glass and an electronic balance, you would weigh out a specific mass of solute. So you would weigh out our sodium carbonate on the clock glass. Then you transfer to a beaker containing some deionized water. Has to be deionized water, okay? And then using a wash bottle of deionized water, wash any traces of your sodium carbonate from the clock glass down into the beaker, okay? Stir, top, dissolve. We have these procedures, and actually page 91 of the revision book does it out fairly well in the diagrams. Then using a funnel, you're going to transfer the contents of the beaker to a clean volumetric flask, okay? Don't forget, using a wash bottle of deionized water, rinse out the beaker and add the rinsings to the flask, okay? Add deionized water then using a wash bottle until the bottom of the meniscus of the solution is 1 centimetre from the graduation mark. Remove the funnel. Don't forget to remove the funnel. Otherwise, drops will drop down from the funnel into your volumetric flask. Removing the funnel and then using a dropper, add deionized water until the bottom of the meniscus is at the graduation mark. Read at eye level. Stopper and invert then 20 times, 30 times until the solution is homogeneous. Now be careful to read back over your answers. So you're saying things like adding deionized water using a dropper until the bottom of the meniscus of the solution is at the graduation mark. Read at eye level. Stopper and invert. So be careful to read over your answers as well, because sometimes when you're writing, you forget to say things that you should be saying. Now, running through the apparatus, this is your pipette. So how do we prepare the pipette for the titration? Well, you rinse with deionized water to clean it, and then you rinse it with some of the base that it's going to contain, some of the solution that it's going to contain. That's to get rid of the water, okay? Because otherwise, what would drops of water remaining in a pipette do to your base solution? They would dilute it. Would you then know the molarity of the base that you were delivering to the conical flask? No, you would not, because you've diluted the molarity of the base. You don't know the M then to fill into your formula. So you must know the volume and the molarity of the base if you're going to be able to calculate the number of moles of base that you've just put into the conical flask. So you must know the V, you must know the M. If you've water in the pipette, you'll dilute your solution. You won't know the M, okay? Using a pipette filler, we don't mouth pipette anymore for health and safety reasons. So using the pipette filler, you fill the pipette until the bottom of the meniscus is at the graduation mark. Make sure there's no air bubbles, that sort of thing. Read at eye level, watch those kind of precautions. And then you transfer the base to the conical flask. And remember that you tip the side of the pipette off the conical flask to make sure that all of the base has been delivered. Don't blow out the last drop. The last drop has been taken into account when the pipette was being manufactured. So look, touch off the side of the beaker. This will remove any, yeah, exactly. Let it drain under gravity, and then don't blow out the last drop because that's taken into account. So you have delivered exactly 25 cubic centimeters of base now to your conical flask, and you know the concentration, you know the molarity, so you will be able to calculate the number of moles of base in that flask. The burette, look, has the tap at the end of it, and look at the area below the tap. The tip of the burette needs to be filled as well, remember. Similarly, you're going to rinse the burette with deionized water, rinse the burette with the acid, some of the solution it's going to contain, to get rid of the water, because again, otherwise you'll dilute the acid in the burette and you won't know the dilution factor, so you won't be able to accurately calculate the molarity of you won't know the molarity of the acid in the burette then. Using a small funnel then, you're going to fill the burette until with acid above the zero. Remember we talked about filling above the zero. Remove the funnel, open the tap, allow the acid to pour through until the bottom of the meniscus is at the graduation mark, reading at eye level. Stop the tap then, or close the tap, and this ensures the tip of the burette is full. And remember, 50 cubic centimeters in the burette at the beginning. So if you're going to be able to measure accurately the volume of acid that was needed to neutralise the base, you needed to have 50 in that at the start, so that you have an accurate volume then of acid that's needed. Otherwise, if you don't have 50 exactly in there at the start, then you don't know how much acid you had to add to neutralise the base. So ensure the tip is full, because that's been taken into account when the burette was graduated. Conical flask then is where where it occurs. So the design of the conical flask, if they ask you anything about the narrow neck, when you're swirling, you won't avoid splashing of solution out that way. Before you use it, you rinse it with deionized water only. You do not rinse out the conical flask with the solution that it's about to contain. Now, why do you rinse it out with deionized water? To clean it. If you rinsed that out with base, then you would have a few drops of base remaining in the conical flask, okay? What would that then do? Well, when you go then to add 25 cubic centimeters of base from the pipette, you've already got base in the conical flask. So what's that going? Do you know the volume of base in the conical flask starting off? No, you don't. So you need to know the volume of base and the molarity of the base if you're going to figure out the number of moles of base in that flask at the start. You know the volume if you've accurately used a pipette to deliver exactly 25 mils of base to that conical flask. If you've washed the flask out with base, there's base in the flask at the start. Then you add another 25 mils, you don't know how much base you have in the conical flask at the start of your titration, okay? Now they might ask you is, if you've added base to the conical flask, what you don't know then is the exact volume. That's what you need to consider. The exact volume is not known. Now you will have water in that flask at the start. Will the water dilute the base? Yes, it will. Will it change the number of moles of base that you have delivered to the flask? No, it won't. It will not change the number of moles of sodium carbonate because it's just water. Yes, you'll dilute the solution, of course you will. If there's water in the flask, you'll dilute the solution. But it will not change the number of moles of base, and that's what you need to know for your calculation. Thank you.